The quest for fusion, Tokamak magnetic confinement systems and the challenge of power at scale introduction. The challenge of energy as humanity confronts the ongoing challenge of energy production. The intricate interactions of atoms present a tantalizing potential. Nuclear fusion, the sun's power source, holds the promise of an almost infinite source of clean energy. However, replicating this process on Earth is a monumental engineering challenge, rife with technical difficulties, material limitations, and fundamental physics. Central to this endeavor is the Tokamak, a sophisticated device designed to confine hot plasma with powerful magnetic fields. Context: a world craving energy. By the mid-20th century, the world faced a pressing energy crisis. The growing reliance on fossil fuels was accompanied by significant environmental consequences. In response to the urgent need for cleaner energy, engineers and scientists began to explore alternative sources. In the Soviet Union of the 1950s, magnetic confinement for nuclear fusion was pioneered. The Tokamak, standing for toroidal chamber with magnetic coils, emerged as a leading candidate in the search for fusion energy, relying on its geometric plasma configuration and magnetic fields for stability and control. The engineering challenge designing a Tokamak entails numerous challenges. Fusion requires extremely high temperatures, around 150 million degrees Celsius, to enable positively charged atomic nuclei to overcome repulsive forces. At these temperatures, matter turns into plasma, an ionized gas where electrons are separated from nuclei. The critical issue is containing this plasma without it contacting the Tokamak's walls, which would cool it and prevent fusion. To address this, engineers employed magnetic confinement principles. The Tokamak generates strong magnetic fields, creating a magnetic bottle to hold the hot plasma. This approach depends on three interrelated systems: magnetic confinement, heating, and the structural integrity of the Tokamak. Step-by-step approach to the Tokamak design. 1. Magnetic confinement system. The Tokamak has a toroidal chamber for plasma containment. Two types of coils generate the required magnetic fields. Toroidal field coils encircle the torus, while poloidal field coils offer additional vertical stabilization. The arrangement of these coils must balance the forces acting on the plasma. 2. Heating systems. After confinement, plasma must be heated to fusion temperatures. Methods include ohmic heating, neutral beam injection, and radio frequency heating. Ohmic heating induces a current in the plasma, but becomes less efficient at higher temperatures. Thus, neutral beam injection is necessary to achieve the extreme conditions for sustained fusion. 3. Structural design. The Tokamak endures immense forces and temperatures. Engineers select materials based on their ability to withstand high stress and radiation exposure. While many materials can tolerate high temperatures, few endure the energetic neutrons from fusion reactions. Tungsten and carbon composites are common choices for their durability. Key systems and mechanisms. The configuration of magnetic fields is vital. It must achieve stable equilibrium to prevent the plasma from touching reactor walls. Advanced computational models simulate plasma behavior and magnetic field interactions, allowing for precise alignment and strength adjustments, which are crucial for confinement. Real-time magnetic field adjustments through feedback control systems counteract instabilities due to temperature or density fluctuations, showcasing the advanced engineering behind the Tokamak. Difficulties and breakthroughs. Despite decades of research, achieving ignition, a net positive energy output, remains elusive. The ITER project in France aims to demonstrate this capability on a pilot scale, benefiting from insights gained from previous devices like JET and TFTR. Significant challenges included magnet technology for effective operation. Early models struggled with conventional superconducting wires under high fields. ITER employs advanced superconducting materials, achieving higher temperature operations with reduced cooling costs. Iterative development, learning from failures. Tokamak design evolution relies on an iterative learning process from failures. In the early 1990s, TFTR produced a record 10 million watts of fusion power briefly, but sustaining that output required improved heating and confinement strategies. The evolution of plasma behavior understanding has led to enhanced confinement efficiency, exemplifying the trend that every failure yields invaluable insights. Real-world impact and significance. Successfully harnessing fusion energy holds transformative implications. Unlike fossil fuels, fusion offers energy production without environmental harm, utilizing abundant fuel sources like deuterium from seawater. Moreover, fusion waste is less radioactive and shorter-lived than fission. Engineering breakthroughs in Tokamak design and magnetic confinement extend beyond fusion energy, impacting various scientific and engineering fields. Advanced superconducting materials have found applications in medical imaging, particle accelerators, and industry. Conclusion: the road ahead as ITER and future projects progress The insights gained and technologies developed will reshape energy production for decades. The pathway toward practical nuclear fusion is lined with challenges and persistence. The promise of the tokamak represents not just energy generation, it embodies humanity's quest for knowledge, resilience in facing challenges, and commitment to a sustainable future. As engineers and scientists collaborate to unlock fusion's secrets, they bear the weight of technical ambition and the hope for a cleaner, brighter world.